Welcome back to Cloud 42. I'm James. This is just a quick update on the manufacturing progress for the PC boards that I'm going to make available for the Electronic Leadscrew project. You'll remember this board. This is one that I made in a previous video. You'll recall I had the PC board itself manufactured at an offshore fab, and then I placed and reflow soldered all of the components by hand, just with solder paste stencil and tweezers and a shop-built reflow oven. Now, I have been spending some time trying to figure out just how efficient I can make that process and how efficiently I can make these boards. I did 3 of them and timed it, and it took me 25 minutes to place all of the components. If I throw in a healthy dose of optimism and some organization and some sort of pipelining, I think the best that I could ever do would be to get these down to the point where it took me 5 minutes per board to do the placing. And that doesn't include the actual reflow process, which I'm hoping that I could kind of superset with that, and the actual cleaning and inspection and testing. And I think the best that I could possibly do would be 5 minutes a board. And that is very optimistic. And so at that kind of level, there's just no way that I could sustain any kind of volume production. Even if I priced it appropriately for that, it would still not be something that I would have the time to do and still produce videos for the channel. So I've decided to go in the direction of having these manufactured entirely by the fab. Now, I was working on a through-hole version of this board, and in fact, there's a design for that out on Circuit Maker if you're really interested. But it is very, very tight, and there are a lot of solder joints, and in the end, I decided that it was just going to be too much trouble. I could make it work, people could solder these things, but there are so many opportunities for mistakes, and even very small mistakes, like mounting a transistor the wrong direction or overheating something, could lead to a lot of trouble and a lot of frustration for a lot of folks. So I decided I'm better off just having these things manufactured. So I have made some changes to the board in the service of easy manufacturability, and I have the first production prototypes back from the fab now. So I'm having these assembled at JLC PCB, which is an assembler in Shenzhen, and they have done a fantastic job of pipelining the PC board manufacturing and assembly process. And maybe I'll do another video on their business model. There are some videos out there on how they actually manufacture the boards, but what I think is really interesting is the way they're changing the scale of the industry from a situation where you would normally have to run thousands or hundreds of thousands of boards to get economy of scale. The way they're using the front-end technology to gang boards together, and more importantly, how they've streamlined the assembly process to be able to do very small orders very efficiently. I'll probably do another video on that because it's fascinating what they've done with the business model. And honestly, somebody in the United States could do this. And if there were an onshore fab that were running a process similar to this, even if the price was double, I would probably pay it just so that I could have the boards manufactured in the US. But that, to my knowledge, is not available. If anyone does know of a fab that can do that, let me know and I'll check them out. So this is just the initial 5 boards that I did as a test run, just to make sure that this process was going to work before I start ordering 100 or more. So these are the first 5 boards, and let's take a look at some of the changes that I had to make. So first off, I have looked at these under a microscope, and I'm pretty happy. The manufacturing looks good. The PC boards look good, you know, same as the ones that I had manufactured before. Quality seems very, very similar. You'll note the green solder mask, and that is just a cost consideration and a limitation on the assembly service at this point. JLC PCB's assembly service has only been available for a week. I actually placed the order for these boards the day after they went live and found some bugs in the process, but it's all good. So let's take a look at some of the changes that I made between the 2 boards. The most obvious thing, if you're just looking at it, is the voltage regulator. And here's the 3-terminal voltage regulator for the 3.3 volt rail on the original board, and you'll note that it is rotated on the new one. And the reason is because I switched to a different voltage regulator part that was more readily available. JLC PCB can do these regulators that I had before, but I switched over to a 1117. It has a different pin out, so it was necessary to rotate it. There's also a change to the way the bypass capacitors work. Rather than just having the bypass capacitor, I also have a resistor in series with it because the 1117 has a minimum ESR on the output bypass to prevent oscillation. So I had to add a little bit of resistance because I didn't want to use a tantalum capacitor. I also swapped out the transistors. The ones on the original are BSS 138 transistors, and these ones are 2N7002 transistors. And this was just a matter of inventory, what they had available. And the way their business model works, the pricing is different depending on which class of component you're using. And we may get into that in a future video, we'll see. But if you'll remember when I did the through-hole prototype, I actually was using the through-hole version of the 2N7002, so I'm quite confident that those are going to work. The other thing I've done is I swapped out the EEPROM. It is still a microchip EEPROM. It is still the same 8-pin package, but the internal organization of the chip is a little bit different. This was originally, I think I used a 4K here. This is an 8K, but it's a slightly different architecture, so there are some code changes. I'm planning on trying to keep the firmware so that it can support both, just so that anybody who went ahead and built a board with the original design will still continue to be able to use that. But this is just a matter of part availability and price. So with all of these changes relative to getting the components domestically and what I was planning on doing, it's taken dollars per board off of the bill of materials. So that's the reason for the changes. The one other change you might not notice right at first is, you note the rings around the through-hole solder points here are round and they are oblong on the new board. And that's just to improve solderability, to get more surface area to get a soldering iron onto. Now that I'm looking at these, there's actually one other difference that I had not anticipated. I'm noting a small hole right here and another one right down here in the corner. I'll go back and look at the design. I don't believe I put those there. I suspect those are fiducials that were put in place to manage the manufacturing process. Well, let me grab some connectors and let's solder one of these up and try it out. I went ahead and ordered enough connectors to make 100 boards. I've only ordered 5 PC boards because I wanted to make sure this was all right before I ordered the rest. But I went ahead and picked up the connectors for 100 boards because that's what I'm planning for an initial production run. These are the power connectors. These are the same surface mount barrel connectors I used to hand solder them before, or to reflow solder them before. Now, I did not get these soldered on at the factory just because they didn't offer that for this type of component. Don't know if that's something they'll be offering in the future, but I figured these are going to be easy enough to solder by hand, so we'll go ahead and just do them by hand. And I'm pretty sure this is going to be pretty straightforward, that anybody with any kind of reasonable soldering iron should be able to do these. And then we've got the connectors for the stepper driver or the servo. So it's the same kind of 2-part Phoenix style connector with the screw terminals. And I've looked at these look pretty good. And then the PC board connectors. Traditionally, in the TI ecosystem, when you make these boards and have the connectors that go down to the launch pads, you use connectors with long tails so that the boards can be stacked. But in this case, they're not going to be stacked, so I went ahead and just got standard female header connectors with the short pins. It turns out that having those long pins on the back side of the board makes it really hard to solder because you got to reach around them with the solder and with the iron. So we'll just use standard length pins for those. Got 200 in the bag here. And then the last thing is the header for the display connector. And I went ahead and switched to a slightly different style. These ones have the plastic beam on the solder side rather than on the top pin sides, so these stick up a little bit higher from the board and don't lay flat. The ones that I was using before, turns out I was having a really hard time because if you soldered them all the way down flush, the connector didn't fit. So we'll try these. I think these will be better. Of course, I only need 5 pins. So we'll clip off 5. Okay, let's start with the power connector. Now this is of course really awkward because I'm trying to work around the cameras, but we will see how this goes. Okay, I've got my iron set to 330 Celsius. We'll try that, put a little flux on the pins just to, a little flux makes everything better. And make sure I get this where you can see it, and let's just try flowing on a little solder and see how this works. It's taking a moment to get a lot of heat into this pad because it's got vias down to the ground plane. Okay, that's not too bad. Okay, I think I'm going to add some thermal relief to the final version of the PC board. This is a 65 watt iron and it's capable of putting out quite a bit of heat. But at this temperature, at 330 Celsius, it is taking a lot of time to get these pads up to temperature. And so I think with a lesser iron, this might be a challenge. Okay, well, that's in. Now that I have the power connector on here, I want to do an initial test of a couple of things. Before I bother soldering everything else, the most important thing here is I want to make sure that the voltage regulator is working properly and putting out the correct voltage, because the last thing I want to do is get this board soldered up, slap it onto my launch pad and fry everything. And since this is a different voltage regulator than I was using, and it is a different configuration on the board, I just want to make sure I didn't make any mistakes. So let's start by just applying power. And we get 2 red LEDs. That's a good sign. So that's the 5 volt and the 3.3 volt. But I'm also going to actually check it. So can you read that meter? I think you can. Okay, so here's a ground. Here's the 5 volt input, 5.2, exactly as I expect, and here's the 3.3, 3.308 volts. Okay, that's good. I'm happy with that, and let's just make sure that the voltage regulator isn't oscillating. Switch this to AC, and 0.0 volts ripple. Great. Oh. Well, I'm glad the connector held. Let me go ahead and pull that out. And let's get some of the other components on the board here. I think I'm going to do the stuff that has to be soldered on the bottom of the board first. So let's put this connector in, and here's a little trick. I'm going to use a clothespin to hold that in place, at least until I get the first couple of pins soldered. Okay, 2 pins soldered. The larger pads are definitely making this easier. Now let's put in the little 5-pin header. I wish I had a clever way to make this easier, but I'm going to start by just tacking one of these by hand. That leaves us with these. And let's tack 2 pins diagonally opposite. Yeah, these shorter pins are much easier to solder for sure than with the long ones in there. The long ones were just constantly getting in the way. I've also only got 15 thousandths solder mask between the pins, and I was worried that was going to be a little bit of a problem, but I was trying to optimize the size of the pad to make it easier to solder, and that seems to have worked. I'm not having any trouble with those at all. 100 mil spacing, and it's an 85 mil pad. This lead-free solder is behaving itself really well. Let's go grab a power supply and a servo and a microcontroller, and let's plug this in and see if it works as well as the original. Before we do anything crazy with the new board, let's just test with one of my existing boards and just make sure that I have everything set up properly. Okay, I've got this all plugged in. I've got the driver back here, power supply is off the side over here where you can't see it. And let me explain a little bit about what you're looking at here. So this is my prototyping board set up with the display panel and the microcontroller and one of the boards that I made before on it. This that's on the breadboard is an encoder simulator. This is an Arduino Pro Mini with code on it that simulates the pulse train for the encoder input. That way I don't have to actually hook this up on the lathe. If I want to do testing, I can actually just do this on the bench. I have a little potentiometer to control the simulated speed of the simulated encoder on the simulated lathe, and that allows me to do bench work on the software without having to worry about a real lathe or causing, injury or damage if something goes wrong. So let's power this up, and the motor should start almost immediately because the simulated encoder input, and it does. So that's running. You can see the simulated RPM here, 62 RPM. Let me speed it up. So this is really great for bench testing, but the whole point here is just to make sure this works before we try our new board. Let's swap in the new board. Okay, I think we're ready. Now, this will be the first time you see it. This will be the first time I see it. I've not actually tried one of these yet. Hey, I see the message. I see the motor turning. Same 61 RPM. Run this all the way up to a simulated 2700. And I think we have a winner. Well, that's all I have for now, at least on camera. Over the next week or so, I'm going to be running these boards through a battery of tests to make sure that they're solid before I then place a larger order and make them available to all of you. I am also working on a spring contact test jig so that I can test the boards without soldering contacts onto them or without soldering on the connectors. So that way I can be sure that every single board works, and I've actually tested it and tested it under load before I ship it out. And I'll probably end up doing another video on that test fixture once I get that figured out. If you're enjoying these videos, please give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.